I think we are recording the video now. Let's start our session number 50 of the International Day of Women in Statistics and Data Science of 2024. We are very happy in participating at this event with this session. It's entitled Empowered Voices, Brazilian award-winning women share their result. And this session is sponsored by the Brazilian Statistics Association. And this session is organized with the aim of inviting 3 distinguished Brazilian women who have earned awards for their work, and they were invited to share with us they awarded works. We have three invited speakers. The first one is Ana Gabriela Silva. She has been honored with the ISI Young Timbergen Award. This award recognizes outstanding papers written by young statisticians, and in the case of the work of Ana Gabriela, the paper addresses significant real-world statistical challenges and contributes to building statistical capacity in developing countries. I'd like to invite Ana to share with us her screen and initiate her speak about her work. Thank you, Ana, for accepting to participate in this session.
Hello, everyone. Thank you, Renato, for the introduction and the invitation. I will share my screen. Are you seeing my screen?
Yes.
Thank you. It's a pleasure to be here. Today, I will be discussing the use of web-based texts in Brazilian Portuguese to classify the main economic activities of companies. But before diving into the technical aspects of my work, I'd like to take a moment to share a bit about my own journey and how many women contribute to it. I think that this will make sense given the theme of this session. So, my name is Ana Gabriela. I'm a white woman. I grew up in a family with many strong women. My mother was a teacher and played a crucial role in my education. She was a solo mother until I was 11. And that's when I met my adoptive father, who also was essential in my education. So now I'm 33 years old and I'm married. I'd like to talk a little more about my academic journey. In 2009, I started my graduation in statistics and actuarial sciences at the University of Rio de Janeiro. In 2014, I completed my graduation and I started working at IBGE, the Brazilian NSO, National Statistics Office. Here I would like to share a piece of information about IBGE. In July of this year, only 27% of IBGE first workforce were women. Despite this number, all my leaders over the past 10 years have been women. They supported me all the way through these years and also to start my master's studies. In 2020, I began my master's studies in statistics at the University of São Paulo. There, I was able to develop and systematize the work that I will present next. Here, I would like to share some data about the University of São Paulo. In 2020, only 22% of postgraduate students at the Institute of Mathematics and Statistics were women. This percentage is close to the proportion of women teachers at the same place. Despite this, my advisor was a woman, the Professor Florencia Leonardi. She was very important during all phases of this study. So when I defended my dissertation, the examiners provided me many important comments and suggestions. In particular, I'm grateful to Professor Denise Brits for all her encouragement and support. After she knew my work, she invited me to participate in this workshop on survey methodology. And there, she suggested that I apply for Jean Timberger Award. So in 2023, I was honored to receive the ISI Jean Timberger Award in Division B for Statistical Systems. I put here some information about the award, but fortunately, the 2025 Jean Timberger Award may be the last year of this award. So, in this occasion, I had the pleasure of sharing the stage with another Brazilian woman, Renata, our chair today. So she also received the Jean Timberger Award, but in Division A. So I'm a Luke woman. I've always had a lot of women around me, and I'm very grateful for it. So now let's return to the technical aspects of my work about the use of web page texts in Brazilian Portuguese for classifying the economic activity of companies. The main goal of this study was to evaluate the use of supervised learning in the context of TestMine to achieve the classification which corresponds to the main economic activity of the companies. For this task, we used data from IBGE, texts from business websites, and data science tools. So the IBGE produced a lot of statistics. Economic statistics are some of them. In this context, we have the annual business surveys. The main goal of these surveys is to investigate information on the basic structural characteristics of a specific business segment in the country. The annual business surveys are composed, among others, by the annual survey of industry, the annual survey of trade, and the annual survey of services. So, for statistics to be informative, it needs to be based on conventions and standards established between producers and the users. In the sense, we have for annual business surveys to serve to public and private planning, to contribute to the calculation of GDP, and with information for monthly and thematic business surveys, they need to be based on conventions and standards. One of these is the National Classification of Economic Activities, CNAE. Annual business surveys basically use the main CNAE. This CNAE is determined by the principal source of revenue. it's one of the determining aspects for building the sample. So select companies based on the incorrect economic classification probably will cause problems in the next steps of the business process, the statistical business process. So the KNAI has a hierarchical structure. Such structures enables different statistical purpose. Classification of economic activities uses an international classification as its reference. The illustration shows an example. So the KNAI has a lot of levels, a section, division, group, class. Here it's possible to note that the greater the number of digits in the code, the more specific is the activity described. About the case study, the predictors were texts obtained via web scraping from business websites in May 2021, and texts from URLs reported in surveys with 2019 as the reference year. About the response variable, it was used the KNAI, the economic classification, obtained from surveys from 2019 as the reference year. In this context, it's important to mention that the predictors are indirectly related to the phenomenon. So the texts were not intended to describe the economic activity of these companies. In addition, there is a time lag between some predictors and the response variable. And more than that, during this period, we lived a COVID crisis. About this last point, a preliminary study showed evidence of the feasibility of using all these variables together, despite a loss in performance. So about the final data set that I used in this study, the response variable comprised 78 final categories. This data set was split in training and test set. It's important to say that that was a case study. So this is a small set of companies compared to the survey sample. The sample was a lot of bigger than the companies in this final data set that I used. So we tested two types of classifiers. We tested a flat classifier. This type of classifier ignores the class hierarchy and predicts the final classes. In this approach, we fitted naive-Bayes, logistic regression, and support vector machines and boosting. We also tested local classifiers. In this case, independent classifiers for each level of the class hierarchy were fitted. We tested naive-Bayes, logistic regression, and support vector machines. About the results, logistic regression presented the best performance using both flat and local classifiers. The results were similar in both approaches when considering all classes. And more than that, the results were similar when we consider two types of measures, the flat measures and the hierarchical measures. So the flat measures are the traditional. They don't consider the hierarchy. And the hierarchical measures give credit to the partially correct classification. So if a classifier predicts the correct division of the KNI, but not the correct group of KNI, is punished differently than the one that doesn't predict the correct division. So in conclusion, we have the feasibility of text collection, despite some setbacks that I didn't share in details here, but as informed, URL not belong to the respondent, URLs referring to websites with texts in languages other than Portuguese, and the difficulty of structuring well-structured texts. Furthermore, the tested algorithms were able to extract partners from texts capable of identifying the main KNI of a company. And it was possible to check the difficulty to choose between a Phyllite classifier and local classifiers because the results were very similar for both approaches. So I understand that a non-trivial task for humans, such as classifying companies by their principal economic activities, will not be trivial for algorithms, even more in a supervised learning context, where algorithms learning from labeled data, but maybe it could be used as an auxiliary tool in the future, I hope. So thank you. I don't know if I passed the time.
Thank you, Anna, for your presentation. We have 2 minutes for one question. If someone of the audience want to make one question, you can write at the chat. In the meantime, I'd like to congratulate you for the presentation and for your work, and also for receiving the Jan Timbergen Award. I was happy to see you mentioned me at your presentation too. It was very nice to meet you at the event last year and be with you at that moment. Congratulations again. We have Leandro sending you congratulations too. And I'd like, let me see, someone, Lani asked if which programs you used and if they are available.
I used Python, it's open source, and Python Backbase. I didn't share my code because the data from IBDE is anonymous. We can share. So, but I use Python, and we can talk about the Backbase specifically after.
Thank you, Anna, once again for your presentation. We have as also one fast question, I think, of Denise. She congratulates you, and she asks if can you let us know if you have continued working in this area?
Yes, thank you for the congratulations. We are studying ways to apply, not exactly this methodology, but another one similar to it. But we aren't using web scraping yet. as we don't have a policy at IBGE for it, for this type of collection. However, we now have an internal group discussing these types of tools and data as texts, the use of data as texts and images. So we are studying ways to use the texts to classify the economic activity of companies, but these texts come from your own forms, our own questionnaires. So we are a step behind, but we are making progress and we are trying. Thank you for
Thank
the
you,
question.
Anna. Well, thank you again for your presentation. We don't have any time, unfortunately, for more questions. So I will invite our next speaker to join us with her video and sharing her screen. In the meanwhile, I will introduce her. For me, it's a pleasure to introduce Daiane Zuanetti from the Federal University of São Carlos. Our second speaker is the winner of the L'Oréal for Women in Science in Brazil award. And this is an award organized by L'Oréal Group in collaboration with the Brazilian Academy of Sciences and the UNESCO. And this award aims to promote and recognize women's contribution to science and to support gender balance in the Brazilian scientific community. Daiane, the audio and video are yours. Thank you again for accepting our invitation to be here at this session.
Hi, everyone. Can you listen me, Renata, and see my slides?
Yes, everything is perfect.
Okay, thanks. Again, hi, everyone. Thanks so much, Renata, for the introduction and for inviting me for this talking in this event. Here, I choose to talk about the data-driven reversible jump algorithms, because it's one of the subjects I have studied in the last 10 years, since my PhD, and even now with some students in the graduation or even the undergraduation. So in applied sciences, we often deal with the model selection problem. That is to identify and select the best model from a subset of potentially suit models. Sometimes this set of models can be very similar and be different just by little details, but in sometimes the set of suitable models can also be very different even in the structure. So consider, for example, mixture models that today it's very useful for clustering and modeling heterogeneous population. We usually need to identify the best numbers of components or clusters, and this number identifies different models inside the mixture models. And sometimes you also have a doubt about if your observations are in fact independent, or if you have some dependency order, first Markov order, for example, or higher order between them. When consider regression and classification models, we usually need to identify a subset of most relevant predictors in a set of thousands or millions of predictors available. And of course, if a predictor is in a model or is out of a model, it guides to different models, and you need to select the most predictive model, the most sweet model for your data based on the number of predictors that you choose and about what predictors you choose for your model in the final. Generally, in both frequentist and Bayesian perspective, we always deal with model selection in two steps. Then first, you fit all the possible suitable models. And in a second step, using model selection criteria, you compare all these models that you were fitted and select the best, following the criterion you choose. For example, you can use AIC, BIC, and their extensions, or in a Bayesian perspective, you can use Bayes factors, DIC, among others, to compare all these fitted models in a second stage and identify the best one. However, this procedure has several limitations. Here, I list some of them. So, the first, this procedure may not be scalable for a large set of complex models, especially when we are dealing with big data sets. Why? Because you need to fit all these possible sweet model before, and it could be a very expensive task. And in a second moment, you calculate, you have the values of the model selection criteria, and you choose the best one. So it can be very expensive and time cost. A second issue is because different selection criteria can guide to different choices. And very often, we don't use just one criterion. We choose a set of selection criteria. We calculate the value of all of them in your fitted model. But sometimes different criteria can guide to different choices, different models. Different model is the best model is different, following different criteria. And another issue is that sometimes some models present very similar values of these selection criteria. Sometimes they are different just in decimal places. And in this situation, the decision for the best, usually it's almost random, or the decision is made by analyzing other features of the model, analyzing other characteristics of the model, the fitted model. For example, analyzing simplicity, analyzing the model that makes more sense for you, and so on. In Bayesian perspective itself, we have a method that we can carry out the estimation and the selection model in the same time in one run, in just one processing, in one stage, and do both things simultaneously. And the method is the reversible jump algorithm proposed by Peter Green in 1995. And the word jump is in the algorithm just means that we can, in just this running of the MCMC, we can switch from one model and its parameter space to another model with its specific parameter space. In the end, if you ensure the convergence of the chain, we can also estimate how likely each tested model is suitable for that observed data. So, in addition of just processing one time the algorithm and visiting all the possible models or visiting the more probable models for your observed data. We have in the end a measure of uncertainty associated with each model. So you can compare how more probable a model is when compared with the other models that you were also visited. In addition, if your interest is prediction, you want to predict new observations, we do not need to choose just one model and a specific model. We can combine the prediction of each model weighted by the uncertainty we have associated with each one. So you have this another advantage. But although we have disadvantage using reversible jump algorithm, it has still been little used in the recent decades, in the recent years. Why? Because depending on the complex of the models we are trying to estimate and compare, the implementation is not easy, mainly because of the calculation and computationally discussing about. Another issue is because many times the algorithm shows a bad mixing, and bad mixing is the dynamic of the chain to visit many models and not being stuck in just one model. So it's the capacity of the algorithm to visit many models without getting stuck. And because of this bad mixing, the consequence is the algorithm usually shows slow convergence. So you can run many iterations of the reversible jump algorithm and do not observe the convergence of the chain. So in this scenario, the data-driven version of the algorithm has shown very good efficient results. Before talking about the data-driven, I will be very fast. Remember the traditional reversible jump algorithm. So you can move from a model M to a new model M star. In a mixture model, for example, K could be the number of components of the current model, and theta is the parameters associated with this current model. And you can move for another mixture model with K star components, could be a smaller or a large number of components, and theta star is the parameter associated with this new model. To build this movie, we have some steps. First, we need to choose the new model, the M star model, to visit. And we choose it with a probability, a prior probability, P of M star. And when you decide, you choose the model to visit, you need to define the parameters associated with this new model. And usually the parameters of this new model, theta star, is a function of the parameters of the current model. It's a function of the theta plus some random variables, U here, that we use to map the parametric dimension of both models, M star and M. The problem is here is that this G function that connect the parameters of both models usually are arbitrary functions decided by the research, mainly because we choose the functions that make sense for our model, for the parameters we need to define, and it needs to be an objective function, because using the inverse of this function, we can come back to the current model through the candidate model. Then this new model, this candidate model, is accepted with this probability, acceptance probability. The L function here is the likelihood, the P is the prior distribution of the parameters, and the Q is the proposal distribution we use it to build the new candidate. So all the probabilities or distributions that are involved in leaving the current model and building the new candidate, the new model, needs to be considered in this proposal distribution. And here we have the Jacobian associated with this G function. This is the deterministic function we use it to connect both the parameters of both models. What's the problem here? Depends the way you define this G function and the way we simulate these U variables to match both parametric dimension, the algorithm is not efficient, it gets stuck in just one model and have a very bad mixing and slow convergence. The idea of the data-driven is to using the data, the observed data, to make this building, the construction of the candidate more efficient and more suitable for the data we observe. So if you build a candidate that is more suitable for the data, we can increase the chance of accepting this new model as a visiting model of our team. In general, data-driven, simplify the methodology. I will show briefly you this case and improve the chain of the mixing of the chain. Here I have just some ideas of the data-driven because of the time, but when we consider mixture model and variable selection, we switch between the models using two types of movie. Burst, so you can perform a burst of a component, a new component in a mixture model, or a burst of a new predictor when you are doing a regression or classification model, or you can carry out a death of a component, then you reduce one component in your model, or you can make a death of a predictor in a classification or regression model. If you decide if you will increase or decrease a component or a predictor, then you have to update the parameters of these new components. So if you decide to add a component in a mixture model, you need to simulate the parameters of this component. And if you, your choice is to increase a predictor in a regression model, we need to decide what predictor we will include in that model and simulate the regression coefficient that is associated with this new predictor. And the difference is here is, while in the traditional reversible jump, these new parameters are simulated or defined using deterministic functions between both models. Here we simulated these new parameters through their posterior conditional distribution. That we can, that's using the data to have better numbers, better parameters, and a more suitable candidate model. Here, conjugacy is important to make it efficient, and the movement is accepted with this probability. Notice that's very similar to the traditional reversible jump, except for the Jacobian. Here, we don't have the Jacobian. And why you don't have this? Very shortly, the explanation is because in the data-driven, we change U star by the theta and the U by the theta star. We simulate theta and theta star by the conditional posterior distribution, and the function G is the identity. So the Jacobian is 1. It simplifies the calculation, simplify the computational, and we have better candidates to evaluate if it was accepted or not. Here, just to finish, I brought some results. Here is the result of data-driven in mixture model. So we applied the algorithm to the rolling thumb text data that is available in this manuscript. Seeing the bar plot, we are in doubt about the independence of the data, mainly because just 12 thumb texts were flipped many times, and it can impact the result. And also because we have just flickers making the experiment, and this could introduce dependence in the data. And when we see the bar plot, it was a doubt if it could be described, but just one distribution, or if it was better to have a mixture of model with, I don't know how many components. And the results, very briefly, the algorithm chose a first order model with this posterior probability for the data set. And here we have the posterior probability for the number of components. So that the RJ choose two components, mixture of two binomial distribution. And if you compare with traditional reversible jump, it's almost impossible to choose just one number of components because the posterior probability are very similar between all value of k. It shows us that probably the method stay lost in the number of components, and many of them are almost equally probable, okay? And you can ask me, but if both chains have the same target distribution, the same posterior joint distribution, why do you have some different results? The answer is because this algorithm didn't show convergence with the number of iterations we run. Probably many more iterations would be necessary to verify here some convergence. Here, I cannot show very many details. I have some manuscript that you can check after. Here I have the results for variable selection. And here, just to finish showing these two plots. Here is the trace plot for the number of predictors in the model using the traditional reversible. And here's the trace plot of the k number of predictors using the DRJ, data-driven. So you note that in the data-driven, the chain, it's easier to leave the correct model, that's k with equal to 5, and visit another model, in the same time come back to the correct model. And other side, the reversible jump, the traditional version, get stuck in some models that was wrong models, and get stuck in this for a long period, and this damaging, in its sense, the calculation of the posterior distribution. Here I have the posterior distribution. I want to give you the detail. Here I have my contact. Everybody can write to me for doubts. Thanks so much, Renata.
Thank you, Diane, once again for accepting our invitation. Unfortunately, we don't have time to questions, so I will start introducing our last speaker, Professor Clarice Demetrio. She is our invited because she has received the the Association Statistics Award, which is an award to celebrate a prominent Brazilian statistician for their substantial contributions to the advancement of statistical education and research in Brazil. She is the only woman among 11 awardees for this award. So for us, it's a very pleasure to receive you here and have this opportunity to hear you sharing with us your life working. Thank you.
Thank you very much, Renata, for the invitation to present our part of our work. This work is a joint work with Silvia Freitas, Lida Fala, and John Hinde, and we have been working in this area for many years. And let me see how to go next. Well, I can't. Okay. Oof. I went to the end. Don't know why. Well, sugarcane is one of the biggest cultures in Brazil. So Brazil is the largest sugarcane producer in the world. But with it, many problems appear. And one of the problems is the pest of sugarcane, the termites, that can cause lots of damage in sugarcane plants and it decrease the production of sugar, alcohol, etc. But a way to control this pest is to use a fungus called the Beauveria bassiana, and they are always testing new isolators that can be effective to control this pest of sugarcane. And the data that motivated our work came from a completely randomized experiment from entomology department here at ESALC, with 142 isolators, everyone replicated 5 times. Solutions of the isolators were applied to groups of 30 termites kept in plastic petri dishes. And the response variable was the mortality in the groups along 8 days. This type of experiment goes in according to the Sustainable Development Goals 2030, the agenda for this, and at least 4 of those 17 goals are according to this type of experiment. I'm not going to discuss that. A single type of data from this experiment, a single replicate appears like that. It goes from day 1 to 8. We have the observed number of termites dead every single day, and then we can produce the cumulative count and cumulative proportion. This is just for one replicate of isolate 848, and here we have another isolate with the 5 replicators, and we can think that this type of data could be thought as 710 observation, 142 isolated by 5 replicators, or the multinomial observations of length 8, because we are observing during 8 days. So this was the first type of model we used, considering as a multinomial observation, or the days are the categories of the multinomial, and day 9 will be the rest of termite that didn't die. We can see that this is a type of sensory data after day 8. Here, just a sample of 16 isolators. We can see that there is variability between replicators within the isolate, and also there is variability between the isolators. So we wanted to choose isolators that could be applied in the field to control this test. So we want to choose isolators that are less variable and that kill the termites very quickly. Here is just a plot with all the isolators. We can see that vary quite a lot. And as I said, we are interested in the comparison of isolators and select the most effective. That is, the ones which vary less and kills the termites very quickly. For this, we are going to use the little time that kills the insect, kills 50% of the insect. We want to determine which is the little time for killing 50% of the insects. Well, starting with the multinomial model, as I said, our categories are 1 to 9, 1 to 8, the observed ones, and 9, the insects that are left. And we are interested in the cumulative proportions. And for this, we can get from using the multinomial model, we can get the variance covariance of the cumulative proportions given by this expression, and we are calling V gamma IK. For analyzing this type of data, we can use a GLM, a generalized linear model, with a link function. In this case, we are going to use the logit link initially for the cumulative proportion. So we are going to use the cumulative logistic model. As a linear predictor, we can include the isolate specific factors and also the time dependency. For example, we can use it for the linear predictor, a straight line with an intercept that varies per isolate and the slope that also varies with the isolate, the index I, showing that beta 1 and beta 2 are varying with the isolators, allowing different curves for different isolates. And this would be my logit link. And then from fitting this model, we can estimate beta 1, beta 2, and get the little time that kills 100 times p percent of the insect is given by this expression, and if p is 50, 100 times p is 50, we will have just the ratio between the intercept and the slope by a negative sign. But as we said, the isolators, they vary a lot, and also the replicators of the isolators, we could see in the plots that they vary a lot. So the assumptions of the multinomial that the probability is fixed for all the isolators is not met. So we need to allow the vector of the multinomial distribution to vary according, in this case, we start with the Dirichlet multinomial. And then we will have a mixed model called Dirichlet multinomial with a variance covariance matrix now, that is the variance covariance of the cumulative probabilities using the multinomial distribution multiplied by an inflation factor. And this model is a generalization of the beta binomial model. Another way of getting the correlation between the replicates of the same isolate is to consider now, instead of varying the probability vector, we vary the predictor vector, allowing one random variable in this predictor, which has mean 0 and the variance sigma I squared. Look, varying with the isolates. And again, we get another variance covariance matrix that is the multinomial variance covariance for the cumulative probabilities with an extra component to get the extra variability of the data. And this would be a generalization of the logistic normal distribution. We here put just a random effect in the intercept, but we can also add a random effect on the slope of the straight line. And with this variance covariance between the random effects. And again, we get a variance covariance matrix that is the multinomial with an extra part to get the extra dispersion caused by the difference. The estimation for the parameters, we use the generalized estimation equation, getting the betas by the iterative solution of this type of system, and the estimates for the variance parameters by a moment-based method. The standard errors or the variance covariance matrix for the beta are of this type, but we can also use the robust matrix based on the sandwich estimator given by this, where we substitute this part by this part here, the residuals. Fitting the models for 30 isolates, we could get all those plots here. And we are interested in those that quickly change. For example, this type of isolate doesn't interested to be selected because you see, it takes lots of time to kill the insects. So we want the ones that go quickly, and also that the variability between the replicates, this one, the variability is smaller than this one, for example. But for this model, we had a surprise because we could see that the parameter estimates were identical, the robust standard errors were identical, and we discussed, we talked to many people, and then took some time to discover that all these were due to some problem with the type of experiment. It was too simple, and the model, the problem was just a problem of a matrix algebra. And this paper was published in 2022, and we could see that the isolates, these green isolates, would be chosen to be replicated to use in the field because they have low variability. Here is sigma squared, here the little dose. So the little dose is, I need a very small, that kill quicker. The time, little time is smaller than the ones for the red ones here. And they have it.
I have to interrupt you. We
I know I didn't have
have
enough
more
time.
time.
Yeah, sorry.
Good.
Sorry, I had less than 15 minutes to present it. Oh, it is okay. Well, I will have some other models, and we are just working on another paper that will work with these other models here. Thank you very much. And if
Thank you, Professor Clarice,
people
for
are
your
interested.
presentation. Thank you all the audience too, for being here and giving us the opportunity to hear about the work of Brazilian award-winning women. Thank you.